Buttons too, if you look there.
So hello, everyone. Many thanks for being here today. We are so happy to have Professor Vipin Kumar. He is from the Department of Computer Science and Engineering. He is he has been the William Norris Grant Chair of the department since 2005 and named a Regents Professor in 2015. His research has been cited more than 127,000 times. And he has been named a IEEE Fellow in 2000 and received the IEEE Technical Achievement Award in 2005 and received the Association for Computing Machinery Special Interest Group on Knowledge Discovery and Data Mining Innovation Award. We're pleased to have you here. Thank you.
Thank you. Happy to be here and talk about the AI revolution that we are living in and how it's catalyzing a new era of scientific discovery. So, as you all know, that we are living in the AI revolution, and if it wasn't clear to anyone, it became so about 2.5 years ago that ChatGPT showed up unannounced. And then last year, about the same time, almost November of 2024, the 2 prizes in physics and chemistry were awarded for people primarily for their work in AI. And what is clear to us is that the AI is poised to fundamentally advance the human capabilities. We can already feel that. And what I want to remind everybody is that this revolution that we're living in is driven by growth in 3 different areas, increasingly more powerful computing, larger and larger data sets, and newer and newer algorithms. And these things just didn't show up at our doorstep just a few years ago. With ChatGPT, this progress has been happening for well over 7 decades. But what we can say is that progress has been happening, but the progress actually has been accelerating and intermingling, with different ideas. And this is sort of what I want to sort of spend a couple of minutes on giving you sort of the history. That is the term we use. Everybody talks about AI, artificial intelligence. The term actually was coined in 1956, just about 70 years ago, and then there was a second different, and the focus of this the series on artificial intelligence was on symbolic AI, mimicking human intelligence. And at the same time, there was another thread that sort of progressed, which was sort of inspired by brain, by how the computing is done in the brain, completely different way of doing computation paradigm. And that also had its first major milestone in 1957, just about 70 years ago, perceptron, which is really the first generation of neural networks whose revolution that we're living in today. And for a long time, for many, many decades, the AI thread overshadowed the neural network thread for almost 60 of these decades. And then it sort of came up with vengeance in 2012. And now we're all living in the neural network world, but it's called AI. And it's all enabled by a combination of things that have happened all along in between. Sometimes we call it as big data analytics, and so forth. So it's a very exciting time to be in the field. And the relevance for scientific computing, relevant for sciences, was already recognized almost 15 to 20 years ago. You can sort of see the middle part here, the cover of Nature and Science with data. In the 90s, between 90s and 2012, this whole thing used to be called big data. You wouldn't hear the term AI. And you can sort of see that in 2012, the White House came up with this big data initiative. And if you go look at the entire initiative, there's not a single mention of artificial intelligence. It's all about data, big data analytics. And already at that time, people knew that these algorithms are really powerful and they can really do wonderful things for us. But then what happened was in 2012, Because of the success in the big data column, large data sets were becoming available, more and more computing power became available, the GPUs and the faster computing was becoming available. Then as a result, an algorithm for neural network built in 1989, look at the first column, convolution neural network, was able to use the data and computing that sort of came about in the previous 25 years. And it was able to show for the first time that these ideas that have been sitting around for 40 years actually are very, very powerful. And since then, the revolution progress has accelerated tremendously. And some of it is, of course, interesting ideas that are just being pulled together. And some of it is ideas being combined with what happened in this field, in our field over the previous 70 years. And I'll give you an example. 2012, of course, AlexNet wins ImageNet Challenge. Everybody considers that to be the watershed moment in the current AI revolution. That's when the deep learning revolution officially started, the third round of it. But then within a year of that, within a year and a half of that almost, in 2013, there was another piece of work that was another sort of a revolution, another piece of revolution that happened, which is sort of reflected in the translation becoming immensely higher quality in 2016. Google Translate would see a big jump, but it was enabled by this piece of work in 2013, which was absolutely fundamental. And what it sort of 2012 revolution happened because very large data sets of images were available. People had labeled them because of the web. Somebody had created millions of images. Does it have a dog? Does it have a cat? Does it have a bicycle? Does it have a human? Does it have a table, chair? And because of so many different images, it was possible to build a very deep network. An algorithm designed in 1989, about 25 years ago, and then people saw the value in these neural networks coming into that. But in 2013, what was done was something completely revolutionary, which is I don't need the labeled data to build powerful machine learning models. I can just look at the data as it exists, look for structure in it, and exploit it. Okay? And just to give you an example, this word-to-vec idea that sort of seems like a very technical term, what it did was you take the text available on the internet, and then you learn from it automatically without knowing anything about the language. You could take it in any language, in English, in French, in Italian, any language for that matter. And all it does is that I'm trying to learn a representation for each word. I'm trying to learn a computer representation of each word. Well, how would I do it? Let me try to learn it by simply taking a sentence, hiding a word, and trying to predict it using the rest of the words. Basically, effectively, it's utilizing the structure in the data. That is when we talk, when we speak, when we communicate, we don't talk gibberish. We don't talk in collection of words that are coming in random. Humans sort of, any communication would involve some structure in the language. Now, how powerful that method became, and of course, it was also enabled by a very smart idea, but also a lot of computing power. Now, once you do this, you can take each word and find a representation for it. And how powerful is the representation? You can take the word for man, or you can take the word for king, subtract the number for man, add the number for woman, and what you get, queen. You take the word for Paris, subtract the word for France, add the word for Italy, you get Rome. So you can literally, the computer learned from this massive amount of data exactly what each of these words sort of mean. And again, that again was followed in just a few years. After that was another big revolution. Computers were supposed to be, as soon as the computers came on, and about 70 years ago, already in 1956, just at the beginning of this field of AI, one of the founding fathers of computer science, Herbert Simon, made a prediction that within 10 years, the computers will beat the best human being in chess. The 10 years came by, of course, nothing happened. Computers were playing chess, but nothing close to humans. 20 years came by. The first time a computer was able to beat the chess champion was in 1996, using a very powerful computer built at Rochester, not too far from here, which was able to evaluate 200 million moves in chess per second. It was massively our computer and a lot of knowledge built into it. It took a lot of effort to do it. Fast forward to 2016, by using the combination of what you see in this column, deep learning, and whatever happened in the last 60 years, and of course, a lot of computing and data, the machine learned to play chess at the level that nobody could beat it just by being told the rules of the game. It would just play against itself and learn how to play it well. This is amazing. This was like a watershed moment. Just after that, 2016 is when the AI became popular. Every country within a matter of a year, every major economy in the world, they had an AI strategy. They knew the AI is something pretty dramatic. And then shortly thereafter, a new design of transformers came in, and the new development in machine learning, and that paved the way for these large language models that you sort of see. And then, of course, they opened the door to all of us in 2023. So this revolution sort of have been happening, as opposed to happening in tens of years, like the AlexNet revolution. The landmark happened after about almost 25 years with the algorithm that invented. Now things are happening every year, every 2 years, right? In the sense that and it's happening very rapidly. And what is amazing is that a lot of these developments are actually, of course, deep, but they are also very simple, very, very simple. The word-to-vec, the revolution that happens, self-supervised learning, be able to learn from the data on its own from the computer. It was done by Jeff Dean. He's the chief scientist at Google. He was already a chief scientist at Google. At that time, he was there for 20 more years. And he came and gave a commencement talk just a few months ago at the University of Minnesota. And I also gave a talk in the college, and a technical talk on the history of AI. And he opened his talk by the honors thesis he did in 1990 at the University of Minnesota. Under my supervision. He sort of said, this is where it started. So the ideas can be very, very simple, but putting them together in a way can do tremendous things. Already, these revolutions are changing the way scientific discovery is done, and that is just changing the game everywhere. So now, it's clear that the advances that have happened in AI are of tremendous power. Everybody in the world is sort of using them. Every discipline is using them. Right now, if you go to any scientific discipline, any scientific community, you will find you'll find people trying to leverage revolution in AI for their own discipline. But most of the advances that you see that people have been using have been driven by the advances that have been made in the context of two domains, computer vision and language modeling. Every single thing that I talked about, I can sort of take you back to, with the exception of game playing, but vast majority of them have been driven by these two domains. And there's an increasing feeling in the community that the next revolution of AI would be driven by a wider class of scientific domains while addressing some of the biggest gaps in the current AI. The current generation of AI is very, very powerful, and yet it can fail miserably in situations that it is not encountered. It doesn't have a sense of what it knows and what it doesn't know, and it's hard to explain, even if it does very, very well. So in 2023, even before, just after the ChatGPT revolution, we held a workshop, and Seva had asked me to organize a workshop at the headquarters in Arlington, Virginia. The workshop was supposed to organize after ChatGPT, but the conception of the workshop happened a year before the ChatGPT revolution. And again, it was sort of driven by the thinking that we need to think about what's the next revolution in AI going to be and how it's going to be driven by and driving the next scientific revolution. And of course, we had that workshop, we had the report, new direction solicitations came out, and then so much had happened around that time that we held a second workshop, follow-up workshop on it, that was focused entirely on generative AI, because generative AI, as a term, didn't exist. I mean, people knew about generative AI, but it was not something that everybody's talking about. Now, generative AI is at everybody's tongue, every company, every corporation, every domain. So So then, so we had a third workshop at McNamara just about a month and a half ago, which was focused entirely on the GenAI for science. And again, just to sort of reflect the fact that yes, the science is going to be driven by this area. So again, just to sort of set the stage again for this thought that we have a growing interest in AI for science, and it's coming in again because of the growing availability of scientific data, and the motivated by high profile breakthroughs that we are able to see, and that is bringing all of us to think about: are we witnessing the dawn of post-theory science? Maybe people don't need to worry about building scientific theories. Maybe the data and computing and algorithm will take care of everything. Okay, so there's an increasing feeling that black box AI models will make existing process models obsolete. I was giving a talk like this about a year ago at Illinois. They had a meeting of the HDR Institute. It's a program that funds these institutes all over the country, and then there are about 6 of those institutes involving several dozen universities from around the country, and they asked me to give a keynote on a topic related to this current talk I'm giving. And the dean of University of Illinois, Dean of Engineering, welcomed the audience, and he was sort of saying, "Hey, are we living in a world where we don't have to teach people differential equations?" Right? So it was like, things are changing so fast. Do we have to change the complete curriculum now? No, it's almost like saying that before the 70s, people have to be really good at how do you do calculations. With calculators, you don't have to worry about that anymore. So there are certain things the technology can make obsolete. So already people were sort of beginning to think, well, the science, what we need to know in science is changing. What I like to sort of remind everybody is that if you use the standard black box machine learning algorithms as they have been available to us for scientific discovery, they can actually they face serious limitations on many, many different fronts. One of them is they require a lot of data. The kinds of data, we have a lot of data in sciences, but not of the kinds that typically are used to train very complex machine learning algorithms. Okay? The other thing is that they can generate results that may look good, but they may be nonsensical. They may be physically inconsistent. Okay? And the bigger thing is that no matter how powerful these machine learning algorithms are, they are only finding patterns in the data that you use for training, which means they can fail to generalize to scenarios that are not seen in the training data. And predictive modeling without clear mechanistic understanding does not advance science, even though, for example, language modeling has become so good. You can converse with ChatGPT like you're talking to a human being, but the science of linguistics hasn't advanced anymore. In the sense that if you go to the linguistic department and say, what have you learned from ChatGPT? They can't really they tell you what happened there. And even more importantly, the decisions involving physical world and environmental systems impact populations of broader ecosystems, and the consequences of missing a flood warning can be far more serious than receiving incorrect recommendation for a hotel or a product. And they have been pretty spectacular failures of blindly applying machines learning into scientific field. So what we have is a situation where we have this world in which we have the traditional scientific world in which people would study the phenomena, build models, first principle based models based on equations and other understanding. But those models are, of course, imperfect because of the limited understanding of the phenomena. And then you have these data science models that seem to work tremendously well as long as you have a lot of data, to the point that you don't even need any understanding of the phenomena for the most part. But they have a trouble that they fail to generalize when the data is not representative. And so both use incomplete sources of information about two key components of knowledge discovery, the theory and data, scientific theory and data. So this is the new direction that we are pursuing. Actually, it started at University of Minnesota, is this paradigm of knowledge-guided machine learning, which effectively combines the power of both of these complementary directions. And it's able to not only use the power of the latest generation of machine learning algorithms, but it's also able to use the knowledge that's inherent in the laws of nature and our understanding of the phenomena, and as a result, combine them and go farther, and also in many ways advance the field of machine learning and science as well. This general direction is also oftentimes referred to as physics-guided machine learning, physics-informed machine learning. Basically, it's just the knowledge is a machine learning that is informed by our understanding of the scientific world. It's a rapidly growing community, and you know there are today you can find KGML being applied to every single discipline. There are all kinds of workshops, meetings. There's a book. The University of Michigan held a 4-day workshop on just this topic. University of Minnesota has been holding workshop on this topic since 2020, since 6 years ago. Most recently, we had one last year, and so forth. And really, you could see many research centers, very large research centers all over the country that are focused on KGML. Ohio State University, for example, has multiple centers that are $10 million to $20 million range, and of course, our group is involved in them. University of Illinois just got. I was in Singapore about 6 weeks ago. They were pushing for a $10 million center on digital twins for agriculture based upon the KGML methodology, and they just got funded just a few weeks ago. So University of Wisconsin has several of these. University of Minnesota has AI Leaf as one of the centered on KGML. So this is a very rich topic and coming up big time. And this activity has been sort of going on for a very long time. And you can see 2016 and earlier, the very first paper that we published this topic was in 2014, Big Data Guide to Understanding Climate Change. This is the first paper from University of Minnesota. And after that, there have been series of papers coming in along these threads from different groups and around the country. And then you can sort of see different topics: chemistry, aquatic sciences, biology, agriculture. All of these areas, you can sort of see huge projects, huge works around the country. And many of them, of course, University of Minnesota is leading them or co-leading them, or our alumni are leading them wherever they are. And a lot of workshops and meetings, a lot of funding agencies announcements, and so forth. This slide just gives you a sort of a technical overview of this, what these different aspects of this paradigm are. How do you use, for example, what are the formats that you use for representing scientific knowledge? Is it PDs or scientific laws or symmetries or knowledge graphs, or just plain mechanistic models? Is your scientific knowledge perfect and complete, or imperfect, or somewhere in between? The form of integration of knowledge and process knowledge and machine learning. Is it centered on processes but using machine learning in a limited way, or is it centered on machine learning using process information in a certain way, or something in between? And you could be integrating knowledge into the learning framework of machine learning and the design of the architecture, or in the pre-training, or be applying it to different use cases in different disciplines. So it's a very rich field. There's an entire 45-minute talk that was presented as a tutorial at the meeting last year at University of Minnesota, accessible from this link that's shown here. So in the rest of this talk, in the next 20 minutes, what I would like to do is just to give you illustration of this paradigm in environmental sciences, which has been my focus. And in environmental sciences, when you model an environmental system, you build process models. You sort of try to model the underlying physics. So for example, if you're trying to model the hydrology of a basin, you're trying to figure out if the rain falls, what happens to it, how much of it goes into the soil, how much of it runs away into the rivers, and eventually cause floods or a lack of rain cause drought. And what you do in that part is you try to model the system. For example, in this case, you may be trying to model the soil. What you're seeing here on the left side is the column of soil. I'm just giving it an illustrative example. And the soil, of course, you can model the soil and its porosity, its ability to absorb water, as a parameter, or you can sort of say, well, different layers of soil can have different amount of capacity to absorb water. So depending on how accurately you want to model the soil, you will have to have many more parameters. The soil is not a single monolithic column, and that sort of tells you that it's never going to be possible to model it perfectly, because there is no limit to how finely you can measure, and more finely you try to represent it, more parameters you need, and the less finely you represent it, you're going to be structurally deficient. So you'll always have incomplete representation of the phenomena, and that's, I'm giving illustration for hydrology, but that applies to any domain that you can think of. You also always have to make scale accuracy trade-off. In some cases, you don't even know. There may be in physics, even if you. So it results in inherent model bias, which you can never recover from. There'll be some mistakes you'll make just because you don't have the information. And even if you are able to parameterize it, you have to find the values of the parameters from the observations, and which is a very expensive and a very inefficient process, which makes it possible to very easily overfit to the data that you have collected. And the idea is that even if you have an area where you have instrumented and collected a lot of data, and then you can collect the data to find the right values of the parameters. And if you don't have a lot of data, you will overfit it. And even if you have a lot of data, you won't be able to leverage the information you learn from the data to a different region or a different place where you don't have any data. You have to start all over again. So it makes very inefficient use of the observation, which means the calibration of a process model in a highly observed entity does not help improve performance on a less observed or unobserved entity. So that becomes a big issue. I mentioned this for environmental system, but this thing applies to every scientific discipline that you can think of. Now, the KGML, being able to build the scientific knowledge and machine learning together, has the potential to address all of these problems. First, it of course handles the problem that you can work with sparse observations because you're bringing in scientific knowledge, so you are able to go much farther than what you could do just with the observation. You can generalize to unseen scenarios because you have the laws built into the machine learning algorithm. It produces physically consistent results, again, for the same reason. But most importantly, it also addresses this very major deficiency of the process models, that we can leverage information from highly observed entities to provide high quality prediction in an unobserved and sparsely observed entity. This is the unique feature about machine learning, that you can learn something and then you can transfer it somewhere else. So there are ways in which machine learning can generalize better than the process models, and vice versa. KGML allows us to bring both of them together. And again, I'm illustrating this, the ability to transfer information in a more graphic way here. And again, this is just a caricature here. What you're seeing here is each of these rows is an entity for which you may be making prediction, and the X dimension is time. And the green entities are the one for which you have a lot of data. And for each one of them, you may be able to be building a model that makes extrapolation in time, prediction in time into the future. But even more importantly, the big question is, can you learn from the green regions and then go to the pink regions, which you have never seen before in both space and time? And this ability to transfer knowledge across in time and space is a unique feature of this paradigm. And it's also a unique feature of the kinds of models that are at your desk now, for a little bit of a payment every month, which sort of allows you to, you use the LLMs. Essentially, they're doing something very, very similar. So in here, I have grouped a sample of the different projects that we're doing in our group. And 4 different products. I know they being able to, and again, some of this work goes back 20 years. Some of this work is very, very new. If you look at this top left quadrant, this is about identifying patterns in global data. So when I say global, I'm talking about global means the around the Earth. And you see the example on the top left, extreme top left, being able to identify teleconnections, the relationship between different components of the climate systems automatically. If you look at the top left corner, but just underneath it is the ocean eddy dynamics, which is looking at the satellite data to figure out exactly how the ocean currents are moving from one place to the other extremely difficult problem because if you want to do that, you have to put a buoy in a cloud over the ocean, and then depending on how the buoy is moving, you will sort of know exactly how the ocean currents are moving. Being able to do that automatically from this data set, it's very, very hard. So this one of our first papers, which led to this paradigm of not theory-guided machine learning, KGML, was driven by the associative dynamics work, which we started doing in about 15 years ago in 2010, which was how do you look at this incomplete data set coming from the altimetry from the satellite, and how do you know exactly how these ocean eddies are moving them? Because the data was very noisy. So it forced us to think about how do you bring in the understanding of how these eddies move around and what the features are, and combine them with the machine learning paradigm to build for the first time, a global data set that was made available to the oceanographer and became a part of the Nature Scientific Data Journal. And to the right of it, you should see a very similar approach being produced for dynamics for the first time, a global data set for all of the surface bodies on the Earth and how they're changing. And it turned out that the data set produced about 750,000 water bodies for the whole globe in the region below 60 degrees, that you sort of see the blue region. And every single body that is larger than 1/10 of a square kilometer is present there. And when this data set was released about 4 years ago, the newspapers called and sort of said, well, how many do you have in Minnesota? And I had my student do the subsetting. It was, of course, data set produced at MSI right here. And it turned out there are 11,000 a few hundred lakes larger than 10 hectares in Minnesota. So we are a land of 10,000 lakes. Now we can quantify. If the lakes are less than 10 hectares, yes, we are we're the land of a little bit more than 10,000. If you reduce the size a little bit more, it'll be in more lakes, depending on how big a area. So basically, these data sets are unique, and we were able to produce them right here at the University of Minnesota, saying here, right here, for the entire globe. And in the same quadrant, the upper right corner is the crop maps on a very large scale. That is, how do you know which pixel, which location in the world is growing what food? And the USDA produces for the United States crop maps every year. And what that graphic is showing you is that you can improve upon those maps very dramatically by using some of these techniques. So that's the top left corner. Again, work going on for more than 15 years. The top right corner is the work that got started in collaboration with USGS after we published our second paper on the KGML paradigm, this whole paradigm that you really need to bring in scientific knowledge and machine learning together. As soon as that paper was published, these people read it in Madison, Wisconsin, and they started coming here every 3 months. They brought their team here, and then collaboration started. And because the USGS is responsible for monitoring the health of about 186,000 lakes and thousands of rivers around the country. And they have very limited, they have data, but they have data, and they have the most data than any other agency have for this ecosystem. But the data is limited, and it has all the issues that we talked about earlier. So then the series of work started in which we started building these models in which the process models and machine learning could be brought together. And a series of very first thing that happened there, for the first time, we were able to show that this method that combined both physics and machine learning can generalize to scenarios that have never been seen before, whereas either one of the paradigms would fail. So you see in the graphic on the top right corner, a demonstration that if you have a method that is combining both machine learning and process knowledge, it's better than the either one. But what is most interesting is if you look at the second part of the thing, is that if you show them scenarios that have never been seen, and what was done here was all of these scenarios were shown data only for the 3 seasons, but they were kept the data for the summer away. And the evaluation was done in summer. And it turned out that even the process model became very bad in the summer because the calibration was done on the other season. Machine learning model, pure machine learning model, were of course very poor. But the method that combined the both ideas actually did extremely well. So that sort of shows you the power of combining. But the top right corner of this graphic tells you one of the most dramatic results that USGS, we were able to produce jointly with USGS. The work was done, of course, by the PhD student in computer science who graduated 2 years ago. And what you're showing in the top right corner is the temperature dynamics. Of course, you won't be able to see very much detail here of all of the 186,000 lakes in the US, whereas data is available only for about 12,000 of them. So previous to this work, you have lakes for which you have data, you have a couple of 100 lakes for which you have a pretty good observations, you have about 12,000 lakes for which you have some observations, and for the remaining ones you have absolutely nothing. So how does the scientific community know? How does the US agencies know what's happening to this lake? What's their health? How are they changing? How are they responding to changing climate? And this work of being able to build KGML models from where you can observe and extrapolate it to where you don't have any information or little information was able to produce this unique data set on the top right corner. And on the bottom left that you see here is one illustration of a series of work that we have done jointly with USGS, but also with NOAA. NOAA has 13 centers around the country. One of them happens to be in Chanhassen. And the one in Chanhassen covers about 5 different states. And they have hydrologists whose job is to the flood modeling and report any risk of floods every day on the TV. I mean, in the sense that if you turn on your TV during the flood season, if they're giving you a flood warning or flood forecast, it's coming from the group in Chanhassen. And what you're showing here in the top right corner is the ability of this methodology that we built here jointly together in showing the forecast. What you're seeing is the virtual forecast. That is, you're sitting at the real-time prediction, you're looking at zero. Zero means it's the morning time at the TV, the forecaster has to make prediction for the next 7 days, every 6 hours. So the 28 predictions you have to make. And of course, the stars that you're seeing here are the actual observations because it's going back. We can see what really happened in those 7 days. Okay, the blue, the red, and the yellow lines are something that you would have done given the state of the art. And the blue is what we're able to produce by this joint combination of physical knowledge and process knowledge. And you can sort of see that machine 7 days before is able to sort of tell the river is going to crest in about 6 days, and it's going to come down pretty much at the same rate as it's predicting. So this was pretty amazing results. So this sort of gives you the example of what can be done by combining the machine and the scientific knowledge. On the bottom right corner is a piece of work that you're seeing here that focuses on agriculture. And this is the work that, of course, has been going big time in our group for the last 5-6 years. It has roots into some of the work that Jim, we did together with you and Phil Pardy on the big data project, which was funded in 2018, about 7 years ago. And this direction led to a $20 million research project here at the University of Minnesota that's ongoing, AI Leaf, and multiple projects. In addition to this, I mentioned to you the one with Illinois that's being funded by Singapore government. There are 2 very large projects funded at Ohio State. One of them is exactly around this topic. So there are many top projects that are being pursued in our group on this topic. And the center of all of these is to see if we can do a good job of modeling what happens to the carbon cycle as we produce food. As we all know, we need to head to the zero carbon world sometime or the other very soon. And even the production of food produces a lot of greenhouse gases. So we can turn our automobiles into electric vehicles, but if you can't convert if you can't make the agriculture carbon zero, net zero, we are well in trouble because we all need to eat food, right? And it's responsible for about 15% of the global carbon emission. So the projects like these are being funded around the world to see if we can build methods, through which we can change agriculture to a new form in which rather than emitting carbon, it actually puts more carbon into the soil. And that is, the models for building these carbon cycles are extremely complex. They have all of the issues that we talked about. And already this methodology of combining scientific knowledge and machine learning is beginning to show a lot of promise. You see some results here. And then again, at some point I may give better results. Now I'm going to conclude by just making some comments about how this methodology of KGML can turbocharge the Gen AI revolution. And again, I mentioned to you, generative AI was not on people's tongue until just a few years ago, even when they held our first workshop at the NSF headquarters on AI-enabled scientific revolution in March of 2023, 3 months after ChatGPT. There was hardly any mention of generative AI at that time. But a year later, it was all about generative AI. And then today, of course, it's all about generative AI. So the question is, how could this philosophy of combining scientific knowledge and machine learning can even make this revolution go much, much faster? And this is a technical slide. It's sort of telling you exactly what needs to be done to get there, but I'm just going to show you one illustration of it, okay? In a very specific context, that is in the context of geosciences. It's a model, it's geospatial foundation model that's being built, which is specially meant for anything to do with the information that can be observed about the Earth from the satellite. And it's currently this work is being done as part of the AI Leaf, our $20 million center, and of course the MSI is absolutely critical for producing this. And what I'm trying to sort of say in the slide is that the moment the notion of these large language models was found to be so powerful in building things like ChatGPT and Gemini, people started exploring very similar ideas in different scientific fields, including geosciences. And the idea was, well, I can also take a lot of data from geosciences, it's available from satellite, and I could do the same thing that's being done by the other community. And underlying all of this is self-supervision, the concept that I talked to you about Berto Beck, from the Google's chief scientist in 2013. And the idea here is that all I'm going to do is, without knowing anything about the domain, I'm going to take an image you see in the top left corner, I'm going to mask portion of it, black it out, okay, and reconstruct it. And in the process of reconstruction, I'm teaching machine something. Just like I showed you, I take a sentence, hide a word, and I try to make a prediction of it. I'm trying to learn something about the structure in the data. So everybody around the world started doing things like this. So basically the foundation models, most of them are like, take the data, hide something into it, reconstruct it. It's called masked reconstruction. So this is, now you can do this with single modality, single type of data. You can do it with multiple modalities. You can also do what ChatGPT does, next token prediction. That's how you get your responses. You type something and you get responses. It's just literally producing the next token and then continuously. So the idea is that I have data from the past about the environment, and I'm trying to train it to take the next step. Because if I have the data for the last 1 year, I can go to the January of 2024 and say, look at the data for January 24. Now predict me February of 2024, because I know what it is, so I can try to teach it. So most of the models, nearly every one of them, is based upon this very standard ideas of masking and reproducing and looking at the next production, next token, and combining these ideas with different modalities. And very large agencies, NASA and IBM have a big project around this idea. Many other groups around the world have been producing, Google is producing it. But then what we are doing in AI Leap on the right side is we are going deeper into the understanding and how these different modalities interact with each other. That is, you can take the satellite data, you can of course try to build embeddings by simply masking some piece of it or predicting the next generation of it. But the satellite data is also interacting with the weather. If it rains and if there are seeds on the ground, they will sprout and then become green. If there's a fertilizer on the ground, the green things become even faster. Once you harvest, things will come down. So the interaction between weather and the satellite data is being captured more in a more principled way in this new model that we're building. We're calling it knowledge-guided foundation model. And this slide is sort of showing you that it's doing a better job, which is a sort of a technical term. But what I want to show you in some very simple visual terms as to how powerful this concept of bringing scientific knowledge can be. So what you're seeing here on the slide is of course there are 3 different models. The top 2 are the top left corner is the most popular approach. This is the IBM NASA product that they started the work about a year and a half ago. They issued this embedding. They spent literally millions of dollars building this foundation model. They use their vast amount of computing power at NASA and brain power at IBM to build this model. using the very standard way, just the way the word2vec was created. Take images, mask them, reconstruct them, and you learn something about the area, and then you build it. Okay. The second one is just doing the same thing using with multiple modalities. And the bottom left one is the one that was produced here at MSI. And what I want to sort of show you is that the model was built, all the model does in each three cases is that using the past data, which knows nothing about the crop, which knows nothing about, it just takes some random images from the entire Earth and looked at what the satellite data looks like. And in some of these cases, you also happen to know what the weather was, okay? And then as a result of that, you build embeddings. That you look, these embeddings have been built by looking at some data set from some locations somewhere, and actually for this comparison, all of them have data using what 10,000 different locations around the world. Okay? Now, once the embeddings have been created, each one has been created using different way. What we did was we took the locations for which USDA has already specified what crops are growing at those locations. So you're seeing these 6 different colors: corn, rice, tomatoes, cotton, soybean, pistachio. These labels are coming from USDA. USDA issues labels every year, and these locations with these different labels were picked up from locations in California, from Minnesota, Iowa, Tennessee, about half a dozen different tiles around the country, maybe about 8 different tiles around the country. And now what we are showing here is that if these points get mapped into the embedding space, and if the embedding can be reduced down to 2 dimensions for visualization, then you can sort of see that these pixels, these colors, if you see carefully in the top right corner, they are mixed up. But in the bottom right corner, all of these colors are sitting separately. You look at this little thing here, is pistachio. In California, this is pistachio. It's sitting separately from everybody else, whereas this pistachio is being mixed up with cotton somewhere, I guess with cotton here also. If you look at the rice, which is sitting over here, the rice is getting mixed up with the yellow, which is corn. So if you look at carefully any one of these, you will see things being mixed up. Whereas this embedding, which was learned without paying any attention to the crop, it just picked up random locations to train. The embeddings know enough about what's happening on the location that once you create this embedding for each location, it sort of knows that how the weather and the satellite data interact with each other. So this sort of shows the power of how if you bring in the scientific knowledge into this paradigm of generative AI, you can really go much, much farther. So with that, I'm going to conclude by just reminding all of us that advances in AI are opening new frontiers for scientific discovery that go way beyond traditional paradigms of physics-based modeling and simulation. And building reliable, generalizable, interpretable models require bringing both scientific knowledge into the machine learning paradigm. And this infusion of knowledge into machine learning is poised to drive the next revolution in AI, which will transform how we model, predict, and discover. With that, let me stop and thank you for your attention.